Okay, today we will start a new section which is called the L'Hopital's rule. Okay, L'Hopital's rule is the following. Okay, L'Hopital's rule says the following. Suppose we have two functions f and g. F and g are two functions. They are differentiable. Differentiable functions. And g derivative is non-zero near a is non-zero for all x near a. For x near a, except possibly at a, except possibly at a. Okay, then if we have infinity over infinity or 0 over 0, suppose limit x approaches some number a, fx over gx is of the form of the type 0 over 0 or infinity over infinity, then we have limit x approaches a, fx over gx. This limit equal to this limit. They both take derivative. Okay, they both take derivative. X approaches a. Okay. Okay. All right. Some example. Okay. L'Hopital's rule is a rule to deal with limit of the type 0 over 0 or infinity over infinity. So for example, limit x approaches 0, sine x over x. Sine x over x. Remember this limit we already dealt with this thing from geometry. Okay, when we talk about the trig derivatives, then we actually take a long process to prove that this limit is actually 1. Okay, remember this limit is 1. This limit is 1. Okay. So if we apply L'Hopital's rule directly, then so this is as x over 0. Okay, you check as x over 0. We sine x is continuous, so the approach is sine 0, which is 0. Of course, sine x over x over 0. So sine x over x is of the type 0 over 0. Okay, so by L'Hopital's rule, if we apply L'Hopital's rule, you check that the different they are both differentiable. Sine x and x are differentiable, and the denominator has derivative non-vanishing. Okay, near 0. So L'Hopital's rule apply. So you apply L'Hopital's rule here. You check. Now apply L'Hopital's rule. Then what we get is now sine x derivative over x derivative. Now sine x derivative gives us cosine x. Okay, cosine x. Now x derivative gives us 1. Now you check here, this is no longer 0 over 0 anymore. So we don't use L'Hopital rule anymore. So this is the, by continuity, we can use direct substitution, cosine 0, which is 1. Okay, which is 1. Okay. This example says, Remember, we also have linear approximation. Linear approximation. Linear approximation says we can locally approximate a function by its tangent line. We can locally approximate a function by its tangent line. So fx is near fa plus f derivative a x minus a. Now, if you do linear approximation to sine x, near x at x point this thing, sine x at a to be 0. Fx, example, sine x, fx is sine x. Then fa, you check, fa is sine f0, a is 0. With sine 0, which is 0. Now f derivative. Now remember, f derivative is sine derivative, which is cosine x. Okay. Now f derivative at a is f derivative at 0, which is the cosine at 0. Cosine 0 is 1. So if you write down the linear approximation of sine x, the linear approximation, you see, we get sine x is really close to, f0 plus f derivative at 0, x minus 0. Okay, a is 0. So f0 is 0. Now f derivative at 0 is 1. X minus 0 is simply just x. Okay, x. So you see, this is actually x. I.e., this linear approximation says sine x is really close to x. Okay. Now, if these two numbers are really close to each other, then they are similar. Okay. Close means it's harder to distinguish. Okay. Hard to distinguish means they are very similar. I.e., their ratio is close to 1. So sine x, if you develop x, this is close to 1. Okay. Near 1. So this actually what this linear approximation says. We get a same result. Okay. Sometimes we need to do, so this linear approximation says sine x is near x for x near 0. Okay, for x near 0. Now you may ask, do we have better approximation than just linear approximation? Do we have better approximation than linear approximation? The question is, the answer is yes. We can use higher order information to get better approximation. Okay. So for this problem, we can do better. We can get a better approximation. So for this example, find this limit. Limit x sine x minus x over x cubed, x upper 0. Now first check that this limit we can apply law of Piaget. Okay, you check as x upper 0. Okay, sine x minus x upper sine 0 minus 0, which is 0 minus 0, which is 0. Okay. X cubed opposite 0 cubed, which is 0. Okay, and the denominator x cubed derivative is 3x squared, which is non-zero for x near 0, except 0. Okay, except 0, except x equal to 0. So okay, so mean value law of Piaget rule apply. So we can apply law of Piaget rule. Okay, so law of Piaget rule apply. Law of Piaget rule applies. Okay, so we use law of Piaget rule. Then we get apply law of Piaget rule. Then we take denominator, numerator, both take derivative. Okay. Okay. Now, L'Hopital rule, one warning is L'Hopital's rule is you should distinguish this with quotient rule. Okay. Don't confuse yourself with quotient rule. Okay. Sine derivative, we get cosine. Okay. X derivative, we get y. And then 3x squared, we get x cubed with derivative of power, we get a 3x cubed, 3x squared. X opposite a. Now here, this limit, you check. Now if you plug in x by 0, what happens if you plug in x by 0? Now cosine 0 minus 1, which is cosine 0 is 1. 1 minus 1, which is 0. So the denominator's numerator is 0. Now the denominator, if you plug in 0, okay, plug in, which is 3 times 0, which is 0. So this again of the type 0 over 0, okay, 0 over 0. If you use direct substitution, you get a 0 over 0, okay? In this situation, we apply L'Hopital's rule. You can easily check that L'Hopital's rule applies. The denominator and numerator are differentiable, and the derivative does not the derivative of denominator does not vanish for x near a not equal to 0. Here a is 0. So we apply L'Hopital rule. So you can sometimes we may apply L'Hopital rule several times. Okay. We may apply L'Hopital's rules a couple of times. So we apply L'Hopital's rule again. Okay, now cosine x derivative. What's cosine x derivative? Cosine x derivative is negative sine x. Okay, negative sine x. One derivative is 0 by constant rule. Now 3x squared by power, we get a 6x. Okay, 6x. So this we get limit x over 0, negative sine x over 6x. Now sine x over x, we know sine x over x has limit 1, okay? So we factor out the coefficients. Sine x over x. You see, we recover the limit of sine x over x. Now this sine x over x, you can use L'Hopital's rule again. Or you just claim this is just write down directly this one, cosine x over y, x opposite 0, x opposite 0. So this is negative 1 over 6, cosine 0, which is negative 1 over 6. Cosine 0 is 1, okay? So finally, we get this limit is limit x approaches 0, sine x minus x over x cubed is negative 1 over 6, okay? Now, in terms of approximation, what does this say? In terms of approximation, what does this limit tells us? Okay, if you write in this form, sine x minus x over x cubed is really close to 1 over 6. 1 over 6. This is not 1 over 6. 1 over 6 for x near 0. If you write in this term, in this form, sine x multiplied by x cubed, really close to negative 1 over 6. Multiply both sides by x cubed, okay? Multiply both sides by x cubed, okay? Then move terms x, move the term x to the right side of this equation. Then you get this. Okay, then you get a higher order approximation. Okay, now remember in linear approximation, compare with linear approximation. Compare with linear approximation. With linear approximation. Linear approximation says sine x is close to x. You see here, compared with linear approximation, we have an extra term, okay, higher order term. higher order term. Okay. Now this is a compare with linear approximation. This is nonlinear terms. Nonlinear terms. So apply L'Hopital's rule several times, then actually you can get higher order approximation, okay, which is in general better than linear approximation, okay, which in general is better than linear approximation. So L'Hopital's rule actually can give us a better version of linear approximation. It can, in several examples, it can give nonlinear approximation. Okay, you may check how good this nonlinear approximation is. Okay, now for instance, you check it use a calculator. Check it this with a calculator. Try to compare which is better approximation. Okay, for instance, let's do one example. Check the thing with algebra package and see how this approximation is. All right. For instance, we check we check fx. We check this thing. Let fx, we define variable x, define function x, define variable x. Then we define fx to be x minus x cubed over 6. Okay, so this is fx. Then gx, let gx be our sine x. Be sine x. Okay, sine x. Now you see, let's check g 0.01. Okay, so we get this sine x sine 0.01. Okay, you see this is approximation. Remember, this is linear approximation says this is close to this number. Okay, this is close to this number. Now, what if we use gx plug in 0.01? Let f plug in f. F is nonlinear approximation, which is better than linear approximation. So we plug in f, plug in 0.1, 0.001 to f. You see, which is better? Which is better approximation? You see, f, the function value f is close to the function g. Okay, it's close to the function g than just the x term. The x term is actually 0.01. Okay, so we get a better approximation by L'Hopital's rule. Okay, let's go back to this. Okay, so we can use L'Hopital's rule to get a higher order approximation. Okay, now we did it for sine x. Now can we get linear approximation, a higher order approximation of sine x and cosine x? Now here we use L'Hopital's rule 3 times. Now that's actually we can do better. There's no reason to stop at simply at 3. Now if you do it for more times L'Hopital's rule, then you get a better and a better approximation. Okay, you may check this sine x minus x minus 1/6 x cubed over x to the power 5. What this limit is? Here this limit, then you need to use 5 times L'Hopital's rule. 5 times L'Hopital's rule. And see what you get. Here we do not do this problem in class. You may check what is it. I'll leave you as an exercise. Okay, all right. Now we did this approximation for sine. Okay, and then I do cosine x. Okay, cosine x. Example. Limit x approaches 0, cosine x minus 1 over x squared. What is this limit is? Now, first of all, we check as x approaches 0. as x approaches 0. Then we see cosine x minus 1. The numerator approaches cosine 0 minus 1, which is cosine 0 is 1. 1 minus 1, which is 0. Now, of course, x squared approaches 0. So we get cosine x minus 1 over x squared is of the type 0 over 0. Okay, and here denominator derivative does not vanish near 0. Okay, except 0. So we can check derivative is 2x. It's not 0 except at x is 0. So we check that L'Hopital's rule applies. Okay, the condition of L'Hopital's rule applies to this question. Okay, so we can apply L'Hopital's rule. So by L'Hopital's rule, we can. Okay, so we apply L'Hopital's rule. So by L'Hopital's rule, we take a derivative of denominator and a derivative of denominator and numerator. X approaches 0. Okay, now we apply power rule. Denominator is x squared. Its derivative by power, we get 2x. Okay. Now numerator derivative, what do we get? Cosine x derivative, we get sine a negative sine x. Sorry. Then 1 derivative get 0. Okay. So this is limit x approaches 0. Now this is negative sine x over twice x. Okay. Sine x over x, we already know this limit is 1. Okay. So you can use this conclusion. Sine x over x. We did many examples of this. Sine x over x approaches 1 as x approaches 0. Okay. So this actually approaches, use linear probability. You can factor this negative 1/2. So get a so this is negative 1/2. Limit x approaches 0, sine x over x. Or you use just simply L'Hopital's rule again. Okay. Here we just use directly this limit is 1. Okay, so this negative 1/2. So this tells us we have this approximation. Okay, we have this approximation. Limit x approaches 0, cosine x minus 1 over x squared is negative 1/2. Okay, so this means cosine x minus 1 over x squared is near negative 1/2 for x near 0. Okay, i.e., if you multiply both sides by x squared, then multiply both sides by x squared. Multiply both sides by x squared. Then what we get? The left side we get cosine x minus 1. The right side we get negative 1/2 x squared. And then move the term negative 1 to the right side. Then you get a positive 1. So you get a sine cosine x is close to 1 minus x squared. Okay, 1 minus x squared for x near 0. Okay. Now let's check how good this approximation is. Okay, see, okay, so we just redefine fx to be y minus x squared over 2. Gx is cosine x. Now let's see g, the function value at 0.01. So we get a 0.99995. Okay. Now what happens if we get f 0.01? You see we get a 0.99995. Now you see this approximation is really good. Okay. Okay, now this is nonlinear approximation. X squared is higher order 2. Linear approximation, we have at most order 1. Okay, we at most have order 1, but here we have order 2. Now, of course, there's no reason to simply stop at this twice approximation. This example, we actually use twice L'Hopital's rule to get actually x squared. Now, if you use higher order approximation, order 4, then actually you can try to do this example. Maybe let's just do it. Over x to the power 4. Okay, first we check this is 0 over 0. L'Hopital's rule actually applies. The denominator derivative does not vanish except x is 0. So we can apply L'Hopital's rule 0 over 0. You check that we can apply L'Hopital's rule by plugging x to be 0. So you get a 0 over 0. Okay. So check, we get a 0 over 0. Then we apply L'Hopital's rule. Then what we get is x power 4, we differentiate that thing. Now the numerator, we get minus 1 plus x squared divided by 2, denominator. Okay, we apply L'Hopital's rule. Then we differentiate. So this is algebra now. It's algebra. Now cosine x derivative is negative sine x. 1 derivative is 0. 1/2 derivative, 1/2 x squared derivative is actually x. Okay. Now x power 4, then we get a 4x cubed by power rule. Okay. Then what do you see? What do we get is limit x up to 0. So this is, you write the thing as negative sine x minus x over 4 times x cubed. Okay. This is, you factor negative a quarter sine x minus x over x cubed. Now this limit sine x over x minus over x cubed as x over 0. We just did it. Okay, we just did this. Okay, we just did this limit. Did this limit. You check what we did. What do we get? What do we get? What do we get? This limit is, you see, this limit is negative 1 over 6. Okay, this is negative 1 over 6. Okay, this is negative 1 over 6. So we can use direct substitution. Okay, so this is times negative 1 over 6. Okay, so we get a negative 24. Positive 24, sorry. So we can write the thing, limit x up to 0, cosine x minus over x power 4. This is has limit 1 over 24. Then if you write as approximation, then you can get this thing, cosine x minus 1 minus x, 1/2 x squared over x power 4. This is 1 over 24, near 1 over 24. This is approximated by 1 over 24. If you multiply both sides by x power 4, multiply both sides by x power 4. Multiply both sides by x power 4. Then what you get is cosine x minus 1 minus 1/2 x squared can be represented by 1 over 24 x power 4. Okay, if you move the terms y minus x squared to the right, then what you get is cosine x is represented by y minus x squared 1/2 plus 1 over 24 x power 4. Okay. Now this turns out to be an even better approximation of this cosine x. Okay. It turns out that you can do more and more terms, then this approximation becomes better and better. Okay. So the right side is polynomial. Okay. So the right side is polynomial. Now we know polynomial is easy to manipulate. Okay. Polynomials are easier to manipulate because it's algebraic. So it has, you know, multiplication and addition, subtracting, etc. This is algebraic. Now the left side trig in some sense is transcendental. It's transcendental. So you can easily, you know, for instance, how do you compute cosine y? How do you compute cosine y by hand? Okay, it's very hard to compute cosine y by hand. Simply you now without a calculator. Now, however, the right side, if you compute sine plugging x to be y, you get a reasonable approximation. Okay, you get a reasonable approximation. Okay. Okay. For instance, if you compute this thing by hand, how do you compute cosine y by hand? Okay. Let's do it. For instance, without a calculator, cosine y. Let's check cosine y. With a calculator, with the algebra package, very trivial. Now, suppose we don't know this answer cosine y. Okay, suppose we don't know this answer cosine y. 0.5403 is cosine y. Now, how do we compute it by algebra? How do we compute this by algebra? Well, you see the right side is a polynomial. Now, if you assume a polynomial, fx is y minus x squared divided by 2 plus x power 4 divided by 24. Okay, and then this, you may think this f as an approximation of cosine. Okay, so its value at 1, should maybe give us some information, should give some approximation of cosine 1. Okay, now if you plug in 1 to f, then what do you see? What do you get? Now you see you get 0.54. Okay, it's not it is in some sense an approximation. Okay, now the thing is, once you have more and more terms, this approximation will be better and better. Okay, so that by L'Hopital's rule, we actually have an algebraic manner to compute sine x, an algebraic manner to compute cosine x. Okay, so we actually get, okay, for this example, if we have more terms, as we have more higher order degree, as we do more times of L'Hopital's rule, as we can do better estimation if we can find even better approximation by adding more terms, higher degree. Now for cosine, the next degree is degree 6. Okay, for cosine, you see all the terms are even degree, Okay, more terms, etc. So this idea, if you study calculus 2, this idea is pushed further. Okay, it's called, for this example, it's called Maclaurin series. Maclaurin series or Taylor series, i.e., you get a polynomial, so i.e., approximate a function by, something like polynomial. I.e., the idea is we can approximate nice functions Here, nice, you can think it as, differentiable, okay? Differentiable to higher degree. Nice functions by something like a polynomial. Okay, polynomial. It turns out for any continuous function on a bounded interval, we can approximate it as good as we can to just simply use polynomial. Okay. Now to get a better and a better approximation, we need to use higher and higher order degree. Okay, higher power of x. Okay, higher and higher power of x. So we can approximate natural functions by polynomials. Okay, by polynomials. So the above example what we just did is we use polynomials to approximate sine x and cosine x. Okay. Okay. Now more examples. Limit x approaches the 1 ln x over x minus 1. Now you check that as x approaches the 1. So ln 1, if you directly use substitution, ln 1 is actually 0. Okay, 1 minus 1 is simply 0. So this is also type 0 over 0. And you check the denominator derivative, x minus 1 derivative is 1, which is non-zero. So L'Hopital's rule applies. Okay. In theory, we need to check derivative is non-zero, but actually in this course, we don't have some bizarre examples. We need actually check the denominator vanishes. Denominator has derivative vanishes. As long as 0 over 0, in practice, you can just directly apply L'Hopital's rule if you simply get 0 over 0 or infinity over infinity. Okay, so 0 over 0, then we apply L'Hopital's rule. So we take derivative for denominator and numerator. Okay, so ln x derivative we already know from logarithmic differentiation is 1 over x. Okay, now x minus 1 derivative, x derivative is 1, 1 derivative is 0. Now this is no longer 0 over 0 anymore. So you just use direct substitution. We just use direct substitution. So this will be 1 over x is 1 over 1. So this is 1 over 1. Limit x, which is 1. Okay, which is 1. i.e., if you write down as approximation, so this says ln x over x minus 1 is really close to 1. i.e., for x near 1. Okay, i.e. ln x is close to multiply both sides by x minus 1, for x near 1. You can also write it in this form. Now you replace x by x plus 1. Replace x by x plus 1. Okay, so this you get ln x plus 1. Ln 1 plus x, ln 1 plus x. This is really close to replace x by x plus 1. X plus 1 minus 1, which is x. Here, for x near 0. Because we already added 1, so when x is near 0, x plus 1 is near 1. Okay, so i.e. we get ln 1 plus x is really close to x. Okay, now you may ask, do we have higher order approximation. The right side is simply degree 1, so it's linear approximation. So this is actually, if you do linear approximation, then this is exactly the form of linear approximation applied to the function ln 1 plus x. So this is linear approximation. Now you may ask, do we have actually better approximation than simply linear approximation? The thing is, if you do higher order degree 2, then you can get better approximation. Maybe we just do one more time of higher order and see what happens. Okay, so if you do the order 2, so you subtract x, okay? So if this is multiple of x squared, so we just find their difference, find their ratio. Okay, find their ratio, limit x approaches 0. Okay, then we apply, so you check it. This is 0 over 0. 0 over 0. Plugging x to 0, then we get 0 over 0. Okay, so we apply L'Hopital's rule. Now x squared derivative, we get twice x. Now logarithmic differentiation, log, okay, ln 1 plus x has this derivative. Minus x derivative is 1. Now here you check, what do you get is, you use algebra. Here is algebra. If you use algebra, then what you get is common denominator. Y minus 1 plus x over twice x. Okay, so what do you finally get? This is limit x over 0. This is negative x over 1 plus x divided by twice x. Okay, so you get x cancel x, use algebra, x cancel x. So you get a negative 1 plus x multiplied by 2. Now this is no longer 0 over 0. So this you can use direct substitution. So this is negative 2 1 plus 0 1 over z. So this you get negative 1/2. Negative 1/2. Okay. So indeed we get a better approximation. So you see, this says limit 1 plus x minus x over x squared approaches negative 1/2. Negative 1/2. Okay, as x over 0. Okay, so if you write it in as approximation, negative 1/2. Then we multiply both sides by x squared. Okay, so multiply both sides. By x squared. Then you see ln. Move x to the other side. Okay. So indeed, so this is the polynomial. The right side is polynomial. The left side is transcendental ln. Now let's check how good this approximation is. For instance, okay, so let fx be ln 1 plus x. Okay, gx is x minus x squared divided by 2. Okay, divided by 2. Then let's check how good, let's check f. Now x is near 0. We plug in 0.1. Okay, so this is f. Now we plug in to g 0.1. Now they are close. They are close. Now, if we plug in a small number, even smaller number, 0.1, then this approximation turns out to be even better. Now you see F and G, the output of F and G, they are really close, 0.995, 0.00995. Okay. This gives us an approximation, okay, approximation by polynomials, okay. Of course, we can get a higher degree. We can get a higher degree, okay, higher degree approximation. Okay, check. Of course, one can get higher degree using higher orders. One can obtain better approximation. Better approximation by using higher order terms. Okay, higher order terms. Okay, so we get an approximation by algebraic, by polynomials. Okay. So this is 0/0. Sometimes we get infinity over infinity. Infinity over infinity. Let's see this example. X approaches infinity, x squared over e to the x. Now I did not mention that when we apply L'Hopital's rule, the number x approaches a, this a can be infinity. This can be a, this number a can be infinity. Okay, here this x squared approaches infinity as x approaches infinity. E to the x also approaches infinity. So this is the infinity over infinity. Now, L'Hopital rule says if we have a function of the type 0/0 or infinity over infinity, then we can apply L'Hopital rule. Okay, then we can apply L'Hopital's rule. Now, for this example, we apply L'Hopital's rule. Okay, so we apply L'Hopital's rule. And then we work out algebra. E to the x derivative is itself does not change. X squared derivative is twice x. Okay, twice x. Now this again is infinity over infinity. Now infinity over infinity, so we can apply L'Hopital's rule again. Now x, 2x derivative, we get a 2. E to the x derivative is e to the x. Now as x approaches infinity, e to the x approaches the infinity, okay? Now 2 over huge number, okay? 2 over a billion. This is really close to 0. So this limit turns out to be 0. Okay. Now, what does this mean? What does this mean? This actually tells us, that this idea tells us x squared over e to the x approaches 0 as x approaches infinity, as x becomes larger. So this means x squared compared with e to the x is insignificant. Okay, e to the x is dominating x squared, okay. So this exponential function increases really fast, okay, faster than any polynomial, okay. You see e to the x, its derivative does not change. Now polynomial, every time we differentiate, the degree decreases by 1, okay. So for any degree, this limit is 0. Okay. For instance, if you have x cubed e to the x, then you apply 3 times the L'Hopital's rule. Every time the x cubed, it's polynomial. Every time you differentiate by power rule, its degree decreases by 1. Okay. Now e to the x derivative does not change. So finally, e to the x derivative itself, x cubed derivative, going down. Finally, it will, will be degree 0, will becomes constant. And finally, you get a constant over e to the x, like this 2 over e to the x. Okay. Finally, this also represents 0 as x represents infinity. So you see, polynomial is dominated by exponential function. Any polynomial, okay, any polynomial in x is dominated by exponential function e to the x, okay, or e to the x when e is being greater than 1. Okay, exponential function increases really fast, really fast. Okay, so here we have another order. We have another notation, which is a little o notation. Little o notation. Okay, if fx over gx approaches 0 as x approaches infinity, or as x approaches a, then we write as fx is small order of gx. Okay, small order. This definition. Little o. For example, this tells us exponential function is polynomial is little o of e to the x. Okay, polynomial is little o of e to the x. If you study computer science, actually you will see complex. In computer science, there's a subject called complexity theory, i.e., matter how difficult a problem is, by how long you can solve this problem by computer. Now you may see once you have exponential term, you can solve a certain problem by exponential term. Then this means this problem is difficult, it's not solvable. Exponential increase really fast. However, if you can solve this in polynomial term, this consider doable. The best possible case if you have a smaller order of term. Okay. Now let's compute this limit. Log x over x. X approaches infinity. Log x over x as x approaches infinity. Now this again, infinity over infinity as x approaches infinity, log x approaches infinity. So infinity over infinity, we can use L'Hopital's rule. Okay, L'Hopital's rule. Use L'Hopital's rule. Then we take derivative for numerator over derivative for denominator. Now this will be log x derivative is 1 over x. X derivative is 1. So this is the limit x approaches infinity, 1 over x. Now as x becomes large, we're cheating or beating, okay? 1 over that number is really small, so this is 0. This is limit 0, okay? So this tells us limit x, limit of log x over x approaches 0 as x approaches the infinity. Okay, use this little o notation, then we can write as log x is little o of x, little o of x, okay? i.e. log x is smaller than x, okay, smaller than x, dominated by x. Log, logarithmic function, turns out it increases really slow, increases really slow, slower than any polynomial, okay, slower than any polynomial. So for any epsilon to be positive, for any epsilon, small number epsilon, you take any small number, small power, then you find limit. You do this. Actually, you can do better. X epsilon, limit x approaches infinity. Now what you do is, this is again infinity over infinity as x approaches infinity. Okay, any positive power of x approaches infinity, no problem. So if you use Lopes check, we can apply L'Hopital's rule. Then we get log x derivative, x epsilon power derivative. Take limit x approaches infinity. Log x approach, derivative is 1 over x. X to the power epsilon using power rule. Then we get epsilon times x to the power epsilon minus 1. Okay, then we multiply denominator numerator by x. Multiply denominator numerator by x. Okay, x cancel x, so we get a 1. Now this x multiply this x to the power epsilon minus 1. Then we get x to the power epsilon. Now epsilon is fixed. Epsilon is fixed. Epsilon is fixed, a small number, non-zero number. Okay. Now as x to the power epsilon approaches infinity. Okay. And then this huge number multiply epsilon is again huge number because epsilon is fixed. So this turns out to be the limit is 0. Okay. The limit is 0. So we can conclude that log x over x epsilon power for any epsilon positive approaches 0 as x approaches infinity. So log x is small order of x to the any epsilon power, epsilon positive. Okay, so log x is dominated by any power, any positive power of x as x approaches infinity. Okay, more examples. Okay, sometimes we need to do a little algebra trick to apply L'Hopital's rule. For instance, L'Hopital's rule apply to quotient. Now, once you have product, how to now in the form of L'Hopital's rule, in the statement of L'Hopital's rule, it's f over g, limit f over g. It's a quotient. Remember. Now, once we don't have a quotient, then we need to try to construct a quotient. Okay, so if you, the idea is if you have product f times g, then you can write as f times y over g. So it's a f over y over g, or you can flip f. You write f as y over f times g. So this you get g over y over f. Okay, such that you get a quotient. You get a quotient. Okay. So let's see this example. Limit x approaches 0 plus x times log x. Now remember, log x approaches negative infinity. Remember, log x approaches negative infinity as x approaches positive. So the graph looks like, remember the graph of log x. So this, as x approaches 0 from positive side, you see the graph, goes down to negative infinity. So now log x approaches a huge number, x approaches a small number close to 0, then which is dominating when we take their product, which dominates the other factor. Now here, this is the product. We cannot directly apply L'Hopital's rule. Okay, so what we do is we try to write it as a fraction. Try to write the thing as a fraction. You may ask, okay, here this product, how do we flip? Which factor do we flip? Now, if you don't know which to flip, then you flip a both. Okay, then you flip a both and check which one works. Actually, you can, what we flip is, we flip x. We flip x. This is the, we flip x. If you flip the other, it does not work. It doesn't work. Okay, so we flip x. Now this is the infinity over infinity now. Infinity over infinity. 1 over x over infinity. Infinity over infinity, then we can apply L'Hopital's rule. Then log x derivative, we get a log x derivative. Now 1 over x, then we get 1 over x derivative. Okay, then we use algebra. 1 over x derivative, we get negative 1 over x squared. Now log x derivative, we get 1 over x. 1 over x. We apply L'Hopital's rule. Then we use algebra. Multiply both things by x squared. Multiply both things by x squared. Multiply the thing by x squared. Multiply the thing by x squared. Then what you get is negative 1 x squared times 1 over x. Then we get x. Limit x approaches 0 from positive direction. Now x over negative 1, we get negative x, which has limit as x approaches 0. This is very easy. This has limit 0. Okay. This actually tells us the 0 factor is dominating for this. Okay. So this tells us limit x log x. This is the 0. Okay. Now if you write in this form, limit, remember, once we multiply something, we can write this, we can x log x, we can multiply, we can bring this x as exponent, so this is log x to the power x. Remember, log is continuous. Log is continuous, so you can switch. You can switch limit with log. Okay, log is continuous, so we can switch limit with log. So use this log limit x approaches 0 from plus x to the power x, which is 0. Now, then you see log something is 0. Actually, we know that's a unique solution. Log 1 is 0. Okay, so you actually see limit x approaches 0 from plus x to the power x. This limit is actually 1. Okay, this limit is 1. This limit is 1. Okay, now you may ask, why do you flip x? What happens if you flip 1 over x? If you flip log x? What happens if you write the thing as x over 1 over log x? The thing is, if you do this thing, if you take derivative, if you use L'Hopital's rule, this is the x derivative is 1. Log x derivative, what do you get? Log x squared negative times 1 over x by chain rule. So this is negative x ln squared x. So it's become more complicated. So more complicated. It becomes more complicated, which is not what we want to do. Okay, does not give us a good solution. So we don't want that. So this is why we flip x, not ln x. Okay. This is called 0 times infinity. 0 times infinity, this is called indeterminate products. Okay, this is called indeterminate product. Indeterminate product. For this, we usually just flip f times g. We just flip f or g. Okay, this is also f g over 1 over f. So this is the usual trick that we do with indeterminate product. Okay. Another thing is indeterminate difference. Indeterminate difference. Difference. So, yeah, infinity subtract infinity. Infinity subtract infinity. And remember, infinity has bizarre property. Infinity minus infinity can conclude that infinity minus infinity to be 0. Okay, it's different than 1 minus 1 is 0. So because infinity is different from finite, okay, you should be really careful. It's bizarre property. Let's see some example. Let's see some example. Let's see some example of the thing. Let's see this example. Limit x approaches 1. Y over ln x minus x minus 1. Okay, as x approaches 1, x approaches 1, this approaches the infinity is this y over 0. This approaches the infinity. This y over 0 approaches the infinity. So this infinity over minus infinity. Infinity minus infinity. So this indeterminate form. So what we do is we use common denominator. Okay. We use common denominator to write the thing as common denominator ln x times x minus 1. So this 1 times that thing, we get a x minus 1. And then the factor, the second term, then 1, then we get minus ln x. Okay, minus ln x. Then what we do next is we use this is 0 over 0, 0 over 0. What we do is we use L'Hopital's rule. Derivative. L'Hopital's rule. Okay. Then apply L'Hopital's rule. Then what we get is x derivative is 1, 1 derivative is 0, ln x derivative is 1 over x. And then we use product rule. Product rule, then we get ln x derivative times x minus 1 plus ln x times x minus 1 derivative. Okay, so this will be y over x, y over y minus y over x. So this is the y over x, x minus y. Out of this we get plus ln x, limit x approaches to y. This now again is um, 0 over 0. So if you simplify it a little bit, multiply both sides by x, y multiply x, you get x. Y over x, you multiply x, you get a y. So this you get a x minus y, this you get a x ln x. X approaches the y. Now you, what you do is you use L'Hopital's rule again. Okay. Then what you get is you do a little algebra. Okay, x minus 1 derivative, you get a 1. Okay, you get a 1. X derivative get a 1. 1 derivative get a 0. Then plus x derivative ln x plus x times 1 over x. 1 over x is derivative of ln x derivative. Okay, so this is gonna y minus 0, just forget a 0. So this is plus y times ln x plus y. Ln x derivative is 1 over x. So you multiply x, you get a 1. Limit x approaches the y. So finally, you see, you get a y plus ln y. Ln y is 0, which is ln y is 0. So you get a, this is the actually y half. So the key to deal with difference then is try to write it as a fraction. Try to write it as a fraction. Okay, try to write it as a fraction. Example. Limit n approaches infinity. Let's use x. X approaches infinity. Square root of x plus y minus square root of x. So this is a how do we write it as a fraction? How do we write it as quotient as a fraction? Now, here this difference, the simple. What we do is we multiply its conjugate, and then we divide. So we write the thing as multiply its conjugate. Then divide. So that we just multiply 1. So the value does not change. Then we use difference of two perfect squares. Now x square root cancels square. Okay, you see the key to do this problem is try to make it a fraction by multiplying the conjugate. Multiply the conjugate, okay? So x squared, x plus 1. The numerator x plus 1 minus x, so we get a 1. Square root of x. Okay, now as x approaches infinity, you see the denominator approaches infinity. So you can clearly get this is the 1 over infinity, so this is a 0, okay? The key is try to make it to be a fraction and then apply. So we don't need to apply L'Hopital's rule for this problem because it's simple. Okay. Let me stop here. What happened? What happened? Any questions? Any questions? Sorry. Any questions?